and welcome to this second webinar in a series of two about a very, very intriguing project we did together. Before I introduce our panelists, I want to quickly give you a recap of what we talked about last week. We talked about this very challenging site where we had a building, we're inside a building with a very clean room, no access for us for most of the time. TCE source starting 50, 60 feet below grade here to be remediated to 1 milligram per kilogram. And we had to try to reach the whole source area with heaters. We used thermal conduction heating. These are red sections indicate the heated sections, and we used soil vapor extraction on each of them. So this very, very tricky to reach contaminant. Yes, you can see it here in another rendering. This is the 3D model of the site, the TCE source area down here, the building up here. And we had one area in which we could get access to do drilling, vapor extraction, monitoring, all those things. We talked about that last week. And today we're going to be talking about, in this situation where you have almost no access to this whole area down here I'm circling, how do you convince yourself and your client and your regulators when the remediation is complete, when you've done enough? That's the topic of today. So in order to talk about that, I am going to introduce or ask the two other panelists here to introduce themselves before we get started.
Hi, thank you, Gorm. My name is Bruce Kennington. I'm a principal with Ramboll. I happen to be in Chicago, Illinois, although I practice nationwide in the US and also internationally. But I had the pleasure of working with TRS for implementation of this remedy for a Superfund site, the Pohatcong Valley Groundwater Contamination Superfund Site located in Warren County in New Jersey. We worked together over a period of about roughly 3 years practically from the very beginning. Certainly it began with the design prior to that, but to get this all installed was quite involved. That was discussed on the last webinar series, so I won't go into that, but it was a pleasure to work with TRS to be able to get this done. We had a multitude of challenges in front of us, not only just the geometry here, but also the site setting speaks for itself, and you'll see that in some of the upcoming presentation slides. Back to you, Gorm.
Maybe over to you, Chris.
Yeah, Chris Thomas here. I'm a director of operations for TRS, and I've been working exclusively with soil groundwater mediation for my entire 33-year career now, and exclusively with in situ thermal remediation for 27 of those years. And this was the most technically challenging project I've ever been involved in, and that's just stressful at times, but exhilarating at the same time, and just really proud moment to be involved in this project and get to work with Ramboll and Bruce's team, and just really proud of the work that that the TRS team was with the work they're able to and the way we're able to perform. But it's great to be here to talk about the successful project.
I know you, Chris, I know you had prepared a little video to kind of show again the complexity of the remediation before we get into the multiple lines of evidence stuff. You want me to play that?
Yeah, please do. And to be clear, this was the work of Chad Crownover and Eli Kowalkowski, so thanks to them. But I think it's a great representation of, yeah, the 2D turning to 3D, where you could see the room outlined in blue, the green blob representing the mass of contaminant, and the casings that were installed over about a year and a half. It was just under 5 miles worth of drilling, but you could see that all the casings penetrate and extend through and beyond the green blob to ensure that we had appropriate heating once that system was made operational. What's shown in white here is some of the infrastructure. Again, the only part of this is you can see the footprint of the building, which is an active facility, and the only space that was made available was this former molding room in blue, as Gorm's highlighting here. But we have some of the infrastructure in place, which includes transformers and oil water separators. that were actually in the room along with the rest of our infrastructure. And then to minimize any or further disturbance to the facility, we ran all of that infrastructure through the ceiling, over the roof, and back out to the alleyway where we were able to squeeze in our equipment along the side of the building towards the west. Well, towards the left of the screen, we have the power control units. Yes, thank you, Gorm. And towards the north, we had our SVE support equipment, vapor phase carbons, condensers, cooling towers, you name it. But that's where all the vapor phase control was managed. But it's just it's a great video that the engineering team put together to give an idea of the extent of the major installation components and hurdles we faced when we built this project.
Yeah, if I can add a little bit to what Chris said, Gorm. You know, taking a look at this three-dimensional representation, we used environmental visualization software, EVS, to produce it. It was based on the data set from all the pre-design investigation drilling that we did to come up with high-resolution site characterization data to be able to represent this. But you can see that this geometry of this convoluted, impacted thermal treatment zone drove everything in terms of the design for the thermal treatment system. And without those tools, it would have been very difficult to try to figure out where to get things installed and how to effectively achieve effective treatment throughout the entire zone. So TRS, through implementation, was able to get this all installed. And then we'll talk about, once we get into performance and optimizing the design, different efforts that were taken to make sure that we were achieving the remedial goals through multiple lines of evidence approach with both our client and also the EPA, who is the key regulator in this particular case. The other thing is that this is in the middle of a manufacturing building. They are in active production with production lines. So off to the right of this image here, shown in these polygons that are out there, those are clean areas of the plant where they had production lines that were operating, both during the time we installed this whole system and when we operated it. So that was a real challenge. And we were limited to, just like as Chris mentioned, our operations and installation all had to be done within the constraints of this room shown by these blue walls.
Chris, normally for a site this big, how many soil boring holes do you think we would, for most of your projects, how many boreholes to show that were clean?
Yeah, I guess it is. That's an interesting question, Gorm, because it is highly variable based on the needs and the requirements of the site. But yeah, I would suspect for 27,000 yards, maybe be in the 30 to 40 boring range.
Yeah.
Yeah.
So
here,
in comparison to that, we had a little area here where we could get a small drill rig in, right? And then only during shutdown of the plants for a week or two could we get in along this row. So getting soil samples, let's say we wanted 30 boreholes, we could maybe get less than 10 to do the confirmatory sampling. So that sets up you, Bruce, with that limitation, with that few soil data points, what data did you want and did the client get in order to be confident that we were at the end?
Yeah, no, that's a good question, Gorm. And it's what we were faced at the very outset, given design that we prepared showing the dense infrastructure and doing work inside this operating manufacturing plant. Is recognized early on that you cannot just pick where you want to go and willy-nilly install soil borings to collect post-treatment confirmation data. So given that you had limited access to be able to do it, we talked about with the agency early on, actually as part of our remedial action work plan for implementing this, to utilize a multiple lines of evidence approach, wherein we used 3 additional metrics that included achieving certainly a temperature metric, 90 degrees Celsius at 95% of the temperature monitoring points that we had throughout the thermal treatment volume, but then also energy consumption or energy input that we put into the ground. TRS had a very good thermal model that modeled the heat transfer, heat input, and then also heat losses for this volume. And it being a convoluted volume was important to understand that as part of operating this thermal treatment system. And I would say we'll get into the metrics later on, but we had very good agreement between actually TRS's model and the actual energy that we input into the project to heat the soils to the target temperatures. And then last but not least was with the vapors recovered off of each of the heater groups. There's 3 here. We'll talk about that a little bit coming up. But we were able to achieve asymptotic conditions through vapor recovery. So after heating the soils, achieving temperature and getting all the energy input into the ground, we saw as a result, tailing and asymptotic conditions achieved in the vapors that we're able to recover from the system. So all those together, once we demonstrated that we achieved all of those, metrics in terms of lines of evidence, satisfied that, then we went in and did hot soil borings. But we only had room to install, of all the 3 heater groups, we're only able to install 2 hot soil borings in each heater group for a total of 6.
Yeah. Okay. And Chris, maybe you can explain. I've got a couple of photos. Maybe you can explain some of the things here and how data was collected, if you don't mind.
Sure. Well, this is a classic shot of just how busy the off-limits areas of the formal molding room were. But this photo shows one of the heater fans. I think it might be heater fan 6. But at the base of each of these, where these impact the ground, you can see the angles of the silver casings as they, as you get closer to the right of this photo, the angle gets softer and softer, and that one out in front might be at about 30 degrees. And then as you get further back, that fan shifts out. It's in this pattern as I've seen Gorm do many times when he's developing this concept. But inside that casing is a resistive heater, and it's conductive, or its heater area, is variable and was customized to make sure that we're treating above and below that portion of the green blob. So the heating elements for all one of these is custom, and that played a big role in how we developed our strategy for developing our circuits and how we're monitoring power. But on top of these silver casings, which contain the heaters, is our heater junction box, and this is how we were able to safely connect our heater, or the actual heater, to the circuits. And again, all these are connected to different, some circuits consist of 1 heater up to 5 in certain circumstances. And in the background, you can see how these cables connects back to these silver-backed panels, and these are our breaker panels, which allowed us to isolate the different circuits during operations.
So when you're doing remediation, like if you're injecting or extracting solid vapors, you're always worried about heterogeneity, and maybe one borehole taking all the liquid and other ones not getting any flow. How is that with this technology? How do you know that each of these heater boxes, each of these heaters are getting the right amount of energy? There's like 176 of them. How do you know they're all doing right?
Well, that is the beauty of in situ thermal remediation, that it works regardless, to varying degrees, works regardless of the matrix that it's heating. So we're able to customize the length of that heater to match, where the contamination is, thanks to Ramble's high resolution definition of that blob, the TCE mass. And as we develop our, and each one of those heaters that's custom has a certain resistance, and our engineering group was able to get together and do some mixing and matching to get a consistent resistance for each one of our circuits. And then during operations, we're able to go around and do amp surveys to verify that we're getting the appropriate amount of amperage going to each heater circuit. So in that way, we're able to very precisely calculate how much energy is going to each portion of that heater in this overall massive soil. So we can be very, very precise in our understanding and energy tracking that's going to each heater location for these 170 points throughout the site.
And Bruce, you mentioned, that one of the 3 lines of evidence was the energy, right? So that's where that data came from. We have power at any one time to each of these circuits, and that could all be added up to kilowatt hours delivered every second or every hour, every day. So we have that. You also mentioned vapor extraction, mass removal. How do we keep track of that? We had 3 different groups, and we had like 178 or so heaters, each with vacuum. Did we keep track of the mass removal?
Yeah, so in terms of the metric we established, again, this achieving asymptotic conditions in the concentrations of TCE mass being extracted in the recovered vapors from each group of heaters. So there were 3 groups of heaters for this project, Group A, Group B, and Group C, just the way that we set up the heater setup. And we were able to sample each vapor recovery header. And we actually had a project-specific sampling apparatus that we set up because you've got moisture-laden vapors, TCE plus warm, water vapor coming through the vapor recovery headers from the heater groups, all coming together, and it being very humid, can really complicate your ability to actually discern the actual concentration of organics in that moisture-laden stream. So we actually had a condenser rig set up where we could desiccate or dehumidify our samples, and we could measure it. So we could get routine measurements just using a PID with that desiccated or dehumidified vapor stream. But then we also periodically collected suma canister samples for offsite laboratory analysis, which was quantitative, for TC certainly specifically, and enabled us to calculate the amount of masses being removed over time. So that's how that was accomplished. So we used a PID as a surrogate in between and developed a correlation. For this particular site, we were fortuitously able to do it that way because we only really had, the 99% of the mass of organics coming out was trichloroethylene. There wasn't anything else. There were some trace, amounts of BTEX compounds, but it was all TCE. So we had a pretty good correlation between our PID measurements and the actual laboratory suma canisters. And so that was important because we're able to track how things were going over time. We didn't have to collect hundreds of suma canisters. We're able to use a PID as a surrogate. We could track over time what was taking place so that we knew when we reached a particular milestone, we would collect a suma canister sample and then share those results with the agency. But it provided kind of like more real-time information about how the remedy was progressing. And we'll talk about that later with some of the dashboard reporting that we came up with to help us, bring all the stakeholders along on this journey and showing where we were in their remedial progress.
We'll get there in just a moment when but just the third line of evidence was subsurface temperature, right? And I'll just skip to this is actually a casing that goes down into the formation, and these are temperature sensors that basically sit there all the time and transmit temperature data. So just to summarize, the power and energy measured simply by the electricity applied, the mass removal, the TC constant based on TC concentrations in these vapor recovery lines that were joined together in 3 different locations, group A, B, and C, diminishing returns there. And then of course, temperatures getting to our target temperatures. When those 3 things were there, we could try to convince the regulators, now it's time to do the soil sampling that we could, right? Then Chris, on the outside of the building, we had the equipment, and this is maybe not directly applied because we took the other samples inside the building, but we also had to do some sampling and monitoring out here, right? Basically, the non-condensable gas had to be treated and meet discharge requirements. So, is there anything you want to say about this?
Well, certainly. We're operating the system up to 280 days, I think was the final number. And part of that is just making sure that we're maintaining our support equipment, and 90% of that equipment was located adjacent to the building in the alleyway. Yeah, to the north, you've got water storage tanks and our condensers, and then our blowers in the middle. And then towards the right of this condenser that's right in front of us is our vapor granular activated carbon system to treat the mass that was recovered, the TC mass that was recovered. And
What's
this is where we would collect some more vapor samples as well. What was
what's
that?
this ugly thing in the middle?
Well, I'm glad you pointed that out. Because we're working in an active facility, ensuring that we had vapor control throughout the entire operation was a key element. And we had a number of belt and suspenders approaches to ensure that. One was to make sure that if we did have a failure in our service or electrical service, that this generator would be able to turn on and operate our vapor recovery system to make sure that we had active capture of that system. On top of that, there's an existing subslab depressurization system that was operational. So we had many layers to ensure that not only our own workers were safe, but the plant workers were safe as well.
Yeah, well, I'll add to that, Chris. We also had, again, as part of the belt and suspenders, we had a continuous monitoring system, which was a field, grade gas chromatograph that collected continuous air samples during operation of the thermal treatment system for the duration. And we had the ability to sample at 10 different locations throughout the facility to, verify or to demonstrate to the stakeholders, certainly including the workers in the facility and the facility management, that we didn't have any fugitive emissions that were of concern associated with the thermal treatment operations.
Okay.
One more thing, we actually did, it sounds like a overkill. Okay, you got a backup emergency generator here, but we actually used this thing. We had an electrical storm. There was a power surge through the JCP&L regional transmission lines that came through and fried one of the three-phase terminals going into our main T1 transformer that supplied power to TRS's power control units. And so we were down for a while until we could get that terminal repaired. And the backup generator, started up, did what it was supposed to do, and operated to maintain vapor recovery during that period.
Okay. Awesome. And a reminder to everyone who's listening, there's a Q&A button, and you're more than welcome to type questions or comments at any time. We will see them, but at least at the end of the 31st minutes, we'll get to answer your questions. So I'll ask you, Bruce, now to basically answer this. With all this data coming in, how did you manage presenting that to the regulators and your client in a convincing way so that this could be decisions could be made?
Yeah, we came up with a digitalization solution where we collected all this data and to do it in the old school fashion. Most of us environmental engineers know that, with lots of spreadsheets and pulling data from these different, sources of data and how they're formed. Some data is collected manually, like PID measurements in the field, or that a lot of data is collected automatically. TRS had a SCADA system where the bulk of the RTDs, the temperature sensors we had, they automatically collected that data and stored it on a computer-based SCADA system that we were able to access. Then you also have other forms of data, such as electronic data deliverables from the laboratory with organic vapor results, for example. So a lot of different types of data sets coming all together. And in order to bring, again, as we were going down this journey of remediating this massive TCE and the subsurface soils at the site, we wanted to have the ability where we're bringing the stakeholders along with this, both our client and also the EPA. And when we felt like we were confident that we've established all these metrics and satisfied these lines of evidence, that we were going to be able to terminate operation of portions of the system. We set this up in 3 groups, as I mentioned before, Group A, B, and C heaters. And what that enabled us to do in collecting this data in real time, we utilized a Power BI dashboard. So what's showing up on the screen right now is 1 page of that report. And we're able to more or less have continuous reporting based on the information that was captured, data acquired by the system that we set up and fed it into this Power BI dashboard. So it was a huge time saver, resource saver, provided consistent, high quality reports And these were provided to internally. We looked at them almost daily and weekly, but we provided these on a biweekly basis to the EPA. And it was very helpful, for them to see the progress and show how things were developing, and gave them confidence that by the time we felt that we had achieved these different metrics that we established, they were right there with us. There wasn't any question. So you can see the trends and how things were going. I think for TRS, it really helped in terms of operations, so they knew reliably when we were going to get there. So there wasn't any question. You could see the trajectory with this real-time reporting. So you can see some of the metrics on this page. So you can see energy input. That's gross energy input to the entire system. We have some other panels that show things broken out a little bit more. The temperature metric, which is sensors above 90 degrees Celsius, the average temperature for the entire mass. We have other information like blower runtime. We looked at the extracted vapors over time. What's shown here is just the total mass removed, but we have other dashboards and other pages coming up here that show the trends over time. So this provides again, as a dashboard, a really quick snapshot, easy to digest. You can see what's going on, and it shows all those key important metrics.
Okay.
Back to you, Gorm.
Yep, that's a good one. And we have the 4 pages of the dashboard here, and don't know how much you want to talk about it. Chris, feel free if you want to comment on any of these. This is the energy input, right, for the 3 different groups. They look eerily similar.
Yeah. No, I would say we've been experimenting with digitalization of our data to convey this important information in each one of our jobs to our clients, to make sure they're able to follow on, similar goals that we had here with this. Was our first experience with Power BI, and really enjoyed this tool, and it did streamline our data sharing process. And it was great to have Rambo embrace it and then come up with this visualization tool for the stakeholders. But yeah, fairly standard information that's being presented here. As we talked about earlier, we're able to track the energy applied to each of the different zones, and you can see the time scales. We did start the systems. Group A started about 4 weeks before Group C, but we're able to wrap things up in Group C a little bit sooner because of the spacing, the closer spacing between elements. That was also the area that had the highest level of contamination. But yeah, these were just a great visualization, a great representation of the progress being made in each of the 3 different groups.
You can see the modeled predicted energy input, and then the actual, right? So I must have modeled the Group A one, and someone else modeled the other 2.
This is before we were done.
But yeah, it's never possible to be totally precise. This was pure luck, right? Group A, but then Group B, we used a little bit less than expected. Group C, we used a little bit more, but overall we came within a few percent of the model, which I think we were pretty happy with.
Yeah, to be fair, you're right. This is post remediation, so we were just under, and we're using energy as a guide. Is intended, and I think we would have been closer on C, but I remember we were struggling with driller availability and sequencing to get that samples in, so we thought we'd leave the system operate to just be triply sure that we're going to get hit our soil targets.
Okay, then we look at mass removal as well, and I don't think we should spend a whole lot of time here, but just a quick little reminder, again, 3 different groups, right? And we're looking here at the TCE concentrations over time in all 3 of them. And as you can see, they all 3 have a peak, and then they come down, and then they have what we call the asymptote, right? And we were using that, Bruce, to
That's correct. Yeah. So you see at that top right graph that shows there, we were using PID readings, as I mentioned, which provided a very good surrogate. You can very clearly see the rapid rise when you started driving off the organic vapor as soils heated up and you reach target temperatures. But then there's only so much TC mass there to drive off, and then it tails. Important in the graphs below by each individual heater group, That's a logarithmic scale, by the way, so but if we were to plot it just on a regular, straight, plot without a log scale on it, you'd see a precipitous drop near the end, so you're going from orders of magnitude changes in vapor concentrations and the recovered vapors in each of those instances. So it was very clear in talking to the agency that continued operation wouldn't get us any more mass out of the soils, and that we were done.
Yeah. I do think we also had maybe not a firm target, but we wanted to be at least below 10% of the highest concentration, right? 10%
That's correct.
Or lower, and we were in all three groups.
Yeah, sure. Our metric was essentially 3 consecutive readings. I think at least a week or two apart, where we were within 10% of the previous readings, showing that we were stable and on that asymptote. Yep.
Okay. Excellent. Temperature data. Who wants to talk to that?
I'll let Chris start.
So we had to approach this 2 separate ways. We had all these temperature monitoring points were installed vertically in the treatment zones. In Zone C, which was inside the former molding room, which for the most part we had control of that area, we're able to have those our RTDs, resistance temperature detectors, installed, and they connected directly to our SCADA system. But out in the main plant floor, we had them installed, and they were installed previously by Ramble, the casings were, but we had to install the RTDs and then go out and take weekly measurements using a handheld reader, and then get that data entered into the SCADA system. Again, we had to be sensitive to the real-time plant operations because they're working 2 and 3 shifts at times. But that data was collected routinely and uploaded to or transferred to Ramble, and then Ramble was able to take this information and get it onto the dashboard.
Good. So just a couple of things. This is depth below the surface. It's not a linear scale, right? We jumped down to 60. So we're looking 60 feet to 110 feet down, and these are different depths, and these are the different measurements. If they're green, that means they've already met the target for temperature, right? And if they're not, there may be something going on. So Bruce, these 2 blue ones look quite low. They say 63 and 64, and they're at a location called T18.
Yep.
What did we do about that?
No, so that presented a challenge. It's something that we talked about with TRS quite a bit. You can see in Zone C here that we, at this particular time, this is through mid-April, Zone C had reached temperature uniformly throughout, and so that was a good sign. Lagging slightly behind that was the Group A heaters, or Zone A. You can see some of these RTD sensors at depth are close to 90, but not quite there yet. But reasonably, we were seeing a trajectory for Group A heaters to achieve the metric in relatively short order at this particular time. But we were rightfully concerned about what we were seeing in the Group B heaters, or Zone B, where these sensors were, where we had a significant lag in temperature. You can see there, we're only just above 60 degrees Celsius in a couple of those. I think we have some maps or some figures that can help explain this or illuminate this a little bit further. We're trying to understand why this was happening and what we could do about it. And so we'll go to,
You want this one or the previous one?
This is fine. I think this shows, yes, those sensors there that where the temperatures lagged. There's that one there, and then further to the east, which is at the bottom of this figure, there's the other sensor there within the Group B heater area. Yes, those are 2. You can see both of those are at the very periphery or the edge of the thermal treatment zone as we had mapped it, and also at the edge of where the heaters go. And so that presented a challenge. We also did have some moisture that got into some of the casings, and moisture along with an electrical conductive resistive temperature element with ceramic insulators. You can short circuit against the casing, whatever, and then it trips the breaker and it goes off. So there were some challenges that TRS got on top of, recognizing that we had a lag here, where they were able to dehumidify those heaters and reduce the downtime of those heaters, so they were able to have a consistent heat output. And ultimately, these temperatures did achieve the target temperatures. But it just goes to show you, there's some challenges that you'll be faced with doing thermal treatment, particularly in an environment like this, where you can't locate everything where you want to. We did our best to place them where we thought they would be reasonable. But we had some challenges, but we recognized the problem or the challenge, and came up with a solution.
Yeah.
And one aspect of that, Bruce, if I remember correctly, is that these locations, these casings were put in a year and a half prior to the final definition of the treatment volume. Yeah, so there's a little bit of guesswork we had to make because we wanted to limit the amount of work we did on the main plant floor. There were some things we just had to live with, and I think this was one of those locations. Well,
No, that's true. That's the story. We actually took advantage. These two locations happened to be pre-designed investigation boring locations. Instead of just abandoning the boring, we took the opportunity at the time to put in a steel casing, recognizing that this is where we might want to install some resistant temperature devices in situ to monitor the progress of remediation. So that's where those were. A lot of the other RTDs that we installed were installed, during the actual installation of the thermal treatment system, like the Group C heater area, for example, inside the former molding room. But yeah, you're exactly right, Chris.
I just want to take just a few moments to explain this drawing. Red boxes here show TCE concentrations before thermal remediation, and black boxes and data show after. And the unit is microgram per kilogram. So remember the remediation objective was 1 milligram per kilogram, so 1,000 micrograms per kilogram. So you can see here 44,000 before, 7.5, 3.5. So all of these exceed quite significantly the goal. And then the black boxes you see here right in the middle next to the highest concentrations at the end, we're under 1, so 0.001 milligram per kilogram. So just an example of that. And then the location that wasn't quite warm enough all the time and just got there at the end was here, T18. And you can see we had a sampling location right next to it, and we had to meet 1,000. And as you can see, we're very happy to see that we were more than an order of magnitude below the 1,000 microgram per kilogram goal. So that's important to know. Not only did we have the multiple lines of evidence, we also had extremely convincing soil data at the end, right? Nothing.
Yeah, these are the hot soil boring locations that we spoke about. So
yeah.
there were 6 of them,
Yeah.
2 within each group heater area. So those are shown by these green boxes with the black, data call out boxes on them. Yeah, orders of magnitude below the remedial goal of 1.
So the first question we have is from Chris, another Chris, and he asks, did you look for rebound of TCE concentrations after the system was shut down?
Yes, we did. And the surrogate that we used was in soil vapor, which we continue to monitor presently. And we have not seen significant rebound in the subslab vapors, but we did not collect subsequent rebound samples in the soil matrix. That's just not something that was required. And particularly, I think, in light of the soil results that we did have. Again, these results of these hot soil borings being orders of magnitude below the remedial goal of 1.
Yeah, and you could say rebound is not typically relevant for soil samples, right? Rebound.
That's right.
Rebound is after a remedy, maybe the groundwater is clean, the air is clean, you wait a little, it's no more clean. Where did that contamination come from? If it's rebound, it actually comes out of the soil. And we sampled the soil, and that's the you see here. So
that's a good point, Gorm. So our chief concern, particularly when we discussed this with the EPA, the Albio, the facility operator, and also our client. You're exactly right. Not rebound in soil concentrations, but it's rebound in what it might partition to. In this particular case, this is all in the vadose zone. It's relatively tight, but there is some pore volume, and so you can have diffusion through that matrix, getting into indoor air or going through the subslab and into indoor air. The facility we have still operates a vapor mitigation system. It's important to understand that we treated the soils to 1 but we didn't treat it to zero. So there's still some TCE mass that remains, and we still detect some TCE and subslab vapors at the facility. But the indoor air quality at the facility before and after remediation by thermal treatment, we have almost no issues with indoor air inside the facility whatsoever, whereas before that, we did.
All right, next question for you, Chris, I think, and if you can remember, you're better than me. The question is, what standard was used for the air sampling?
Well, for the air sampling technique?
What standard is used for air sampling? It just says what standard. I don't.
Well, we used analytical method TO15 for analysis of our summa canister samples that were collected.
Yeah.
We used 6-liter summa canisters for doing that work, both of the recovered vapors. Also, when we did our monitoring of indoor air at the facility, we also used 6-liter summa canisters as a standard practice. We also used similar air sampling techniques in accordance with our air permit for our air emissions for what went out the stack. So we had to satisfy our air permit, and that was done by summa canister TO15 analysis.
And we had a certain criteria.
We had limits, yes.
Yeah.
Permit required, emission limits, yes, absolutely. We had no issues with any of those.
All right. The questions coming in are relatively modest today. Maybe you did too good of a job covering the topic. The question that always comes is how much does this all cost? And Bruce, I know you love that question.
Yeah, no, this remedy here to implement this, I would say from design all the way through completion was roughly about 40 million, to treat, this volume of roughly, 24,000, cubic yards beneath the surface. In terms of a metric, a unit comparison of, dollars per cubic yard, I wouldn't use this project as an example. And the reason being is because you can see in the site setting here, the complexity of the installation, operation, and getting the job done was way more involved than you might have with a much more simpler project, like where you're doing thermal treatment in an open field someplace, where you're able to install everything vertically. You don't have interference. You don't have other issues to deal with. So we had a lot of complexities and challenges. That's kind of like the point of our presentation today here, is to sort of talk about the challenges that we faced and then how we're able to come up with solutions to get it done.
Yeah. So there's another question from Nick, which is a real good one. He basically says, how long did it take compared to your estimate? And Bruce, you can maybe explain there was also a real reason to stay on schedule, right? And how did we do?
Yeah, I'll let Chris speak to the time frame in terms of what you guys expected, to be able the time frame to heat the soils and be done. I can speak to the other aspects that were driving the project where we had to get done on time. Yep.
Yeah, time was of the essence. We were under a great deal of pressure to meet our clients' objectives to get this remediation complete, get the source area removed, and get the heck out of the way of the tenant. Our models or the time required to get the energy in the ground for the different areas were based on the volume of the area or the volume of soil to be treated and the contaminant levels. And based on the installation limitation that we talked about previously. So we were able to, since area C or group C was in our control, and we're able to install our heaters vertically, we were able to get our spacing a little bit tighter, and that was also happened to be the area of highest mass. But there we were thinking that would take about 180 days to treat, and we had a little bit of a cushion, 30 to 60 days, just in case. Both area A and B were going to require more time just because there's a cost benefit analysis that needs to occur about how close you get your heaters installed and how much they cost. Because each one of those heaters installed on an angle, most days took about a week. Some would go 200 feet, but they're very expensive, as Bruce pointed out. So we spent a lot of time thinking about the amount of mass in place, the soil volume, and the heating that would be required. As a result, we're going to take about I think we modeled being about 220 days, a little bit longer than what we had planned for C. All told, when we talked about the sampling dates, I think we ran a little bit long at C, but we could have stopped a little bit sooner. But again, there's just logistics involved with actually getting the samples collected, because we had to coordinate that with the facility as well. It's not, we're not in an open field and just collect those samples whenever we feel like. But all told, we were, I think, generally, well, certainly within our time allotted. But we do spend a lot of time worrying about these days and weeks when it comes into operations, because outside of our commitments to our client and our facility, energy is expensive. We want to use that, use those energy dollars as wisely as possible.
Okay.
Yeah, and I can add to what Chris just spoke about, Gorm, you know,
Yeah.
from an overall project perspective. I
Yeah.
mean, we had a schedule with EPA with timeframes in it where work is being performed here, you know, by our client under a consent decree with the US EPA Region 2. And there are stipulated penalties associated with it. Also, you know, to gain access to install all these heaters inside, you know, this L-shaped room inside the building, we had to occupy part of the manufacturing plant space, and that was done under lease by our client. So we were paying money, you know, every month to be able to have access and utilize that room. So it cost our client money, you know, to continue. The longer it took until we were in and out of there, it was an added expense to our client. So we wanted to, you know, get the project done in a timely manner, so we minimized that cost. But then there are also, you know, the risk of penalties on top of this. I would say that with the agency, we also accomplished this work during COVID. So and we did adjust the schedule accordingly based on COVID, because actually the EPA, when we first had the pandemic hit, we went through a period of shutdown for a period of about 4 months until we all figured out, you know, certainly in the United States, how we were going to deal with COVID and how not to spread and infect people. So we came up with procedures ultimately, and we're able to do that. I won't go into any further details there, but we did adjust the schedule based on COVID. But despite all those challenges, and I would say up front, some of the drilling challenges, 75% of this project was drilling.
Yeah.
You know, only 25% of it was actually getting it done and heating the soils, or, you know, some of the treatment system installation work. But this is a drilling project. So that was a real challenge, you know, it would be a challenge for anybody, but certainly with TRS, because you guys are not a drilling company, right? But there was a lot of lessons learned. Had some really qualified people out there, both with our client, who's a global mining company, that, you know, has a lot of people with expertise, certainly in drilling. Our Ramble staff geologists, and then also, you know, the drillers themselves and the TRS staff were able to work together to optimize the drilling. Started out kind of slow. We had some lessons learned, but then, you know, hit our stride and were able to get it done. And then ultimately the project was completed all on time. You know, certainly adjustments to the schedule for COVID. It was also done, you know, on budget, you know, for what was promised. TRS provided a fixed price for getting the job done. That was completed. And then most importantly, we did this entire project installing almost 5 miles of thermoconductive heater casing, 2,500 linear feet, in excess of that, you know, 176 heaters. For all of this work we did with zero lost time, zero, you know, injuries for this project, logging over 160,000 man hours. So, you know, it was an overall success on multiple levels for this project with a combined team. And it was an effort for us working together to do so. That doesn't happen by, you know, happenstance.
Fantastic. Thank you so much, both of you. And I've had the references for peer-reviewed papers we recently got published up here. Anyone who wants more detail can go look these up. And thank you again. And it's been a pleasure. Take care.
Yep. Thanks all. Thanks, Gorm.
Thank you.